Okay, so in the last lecture, we just showed that the integral of f along gamma is equal to capital F of beta minus capital F of alpha if capital F has derivative equal to little f of z, and gamma is a rectifiable path. Gamma A is alpha, gamma B is beta. Okay, so it's alpha, this is beta, it's A and B, gamma, B gamma. Gamma is rectifiable, and F maps alpha beta to complex plane with an image like this, and the capital F prime is equal to little f, right? So this is the integral along gamma, and the result shows that this result only depends on two endpoints, starting and ending point. It does not depend on the realization how we connect this alpha and beta with different path alpha and beta. Once you have capital F prime equal to little f, you always get capital F beta minus capital F alpha. This is gamma. Possibly you have sigma. Sigma is from C to D, and sigma C is alpha. Sigma C is equal to alpha. Sigma D is equal to beta, and F is also defined along sigma. Then we also have such stuff. All right, this is so-called path independence. Path independence. Well, I mentioned this is a slightly different from the, not slightly, big difference between the real analysis, complex analysis. Real analysis, when we say it is path independent, actually there's certain cancellation involved. But here there's no cancellation, it's just independence. All right, okay, so next, here we always say alpha, beta, they're different. What happens if alpha is equal to beta? A curve gamma from AB to C is said to be closed if gamma A is equal to gamma B. So we say it is closed if alpha is equal to beta. Okay? In this case, we call this curve closed. The starting point is equal to the ending point. And clearly, from this result, what is the result? F is defined along this gamma, and the capital F prime is equal to little f, and the gamma itself is rectifiable. Okay? Corollary, let G, gamma, and F satisfy the same hypothesis as in theorem 1.18. 1.18, the result is this. Okay? And if if gamma is closed, gamma A is equal to gamma B, alpha is equal to beta, then the integral of f along gamma is equal to 0 because capital alpha beta minus capital F beta minus capital F alpha is 0. Okay, so that's a trivial, not a trivial, well, it's an observation, right? So, well, here in this problem, we require such so-called primitive or antiderivative exist. So, in this discussion, we require the existence of capital F. But we know that in the calculus, by the fundamental theorem of calculus, each continuous function f, well, this, I mean, from AB to R always has a primitive, right? We know that FTC, the first part, what is a primitive? Capital F of x is equal to the integral from a to x little f t dt. Then capital F prime of x is little f of x. So this always antiderivative. But this is not correct when we talk about complex variable. This is not true when we have complex analysis. Okay, complex analysis, remember this derivative is complex derivative. All right, so when we say it's not true, we're going to pick up example. So let f of z be modulus of z squared. Modulus of z squared is x squared plus y squared. The result is x squared plus y squared. Assume that capital F of z is a primitive of little f of z. Okay, assume we do have. Well, this one is continuous. Capital F is differentiable with a continuous derivative, so capital F is analytic. It's an analytic function, right? Continuously differentiable. Capital F is analytic. Okay, so let capital F of z be capital U of z plus I capital V of z. Capital U of z plus I capital V of z. So you have the real and the imaginary part, right? Then capital prime of z is f of z is x squared plus y squared. It should be u prime. Well, we have several ways to discuss it because we have the Cauchy-Riemann equation. So we get the partial u partial x I partial v partial x, or we have partial v partial y minus partial I partial u partial y, right? The Cauchy-Riemann equation, this one equal to this, equal to the real part. So we have the partial u partial x is equal to partial v partial y is equal to x squared plus y squared. and partial v partial x equal to partial u partial y is equal to 0 because the derivative has no imaginary part, right? So from here, the partial u partial y is 0. Implies that uxy is just ux. It does not have a y. Okay, uxy is just ux. It's independent of y. And partial u partial x is x squared plus y squared, implies u is a function of x and y. The derivative is a function of x and y. Of course, the antiderivative is a function of x and y. It depends on x and y. Here, it only depends on x, so this is contradiction. Correct? It's naturally a contradiction for both. So, it's unless what? Unless the x and y are both 0. Right? So it only has antiderivative when you have a point, but when you have a point, it doesn't have meaning. Okay? So the function cannot have a primitive. Cannot have a primitive. If you do not have a primitive, of course, you cannot apply the theorem 1.18. Theorem 1.18 cannot apply. Cannot be applied. All right, so theorem 1.18 can only be applied if this function does have a primitive. All right, so we finished the section 1 in the Riemann-Stieltjes integral. Now let's see the exercise. Yeah, exercise on page 61, exercise 1. Exercise 6. Exercise 9. 9 is just computation. 9 is okay. 10. 10 is also computation. You can directly compute. And 11. 11, you just do the integral along each side of the polygon. Along one side, you can use a substitution, and not a substitution. You plug in the formula of the segment. You integrate along the parameter. 16. 16 says if you have equivalent rectifiable path, then the total variation are the same. Hmm. 17 says we can always choose the rectifiable. We can always choose the representation of a path from AB to 0, 1. 22 says all the primitives are almost identical up to a constant. And 24, they ask you to prove the integration by parts formula. But anyway, there's no difficult selections. All right, now let's see the next second section. Section 2, power series representation of analytic functions. Power series representation of analytic functions. Power series representation of analytic functions. So 2.01. Proposition. So the first proposition we want to construct the Lebanese rule. We want to construct the Lebanese rule. So this is Lebanese rule. What is a Lebanese rule? Let's check. So let phi from AB cross CD, the domain is a rectangle, to C, be a continuous function. And define G from CD to C by what? We're going to integrate along the x along the y variable. You see, this is AB, x variable. This is a CD. So we have this rectangle, and the CD. For each point, you're going to have this segment. This segment you're going to integrate. So G of t is integral from AB phi st ds. So phi will integrate along this horizontal segment. Right? For each t, you integrate phi along the horizontal segment. For each t, you integrate it. So you will eliminate, integrate x variable. You only leave the y variable. Then you define the function g. And be careful, this phi is a two-dimensional continuous function. Okay, then this is our setting. Then the conclusion is that then G is continuous. G is continuous. So that's our main conclusion. And moreover, if you see this is a phi has a st, if partial phi partial t exists, the partial derivative along the y coordinate exists and is a continuous function on AB cross CD. Okay, then this G, this defined G, this G is continuously differentiable. Continuously differentiable, and the derivative G prime of t is integral from AB phi partial t evaluated at st ds. Okay, evaluated at st ds. This is a so-called Lebanese rule. So what is the Lebanese rule? Lebanese rule actually means the following. Check here. G prime of t is actually the ddt gt, right? G prime is ddt. ddt, you put it here. G is this integral phi st ds. And the Lebanese rule says you can exchange the these two operations, integration and differentiation, you can exchange the integration operation. You can apply the differentiation first inside and then integration second. So that's how the meaning of Lebanese rule. We can exchange those two orders. The reason is that these two coordinates are independent. Well, roughly speaking, the reason is that they are independent. They are not affecting each other. Okay, so that's our idea. Okay, now let's see the proof. Let's see the proof. Actually, we do not prove the main part. G is continuous. This fact is done by the definition of integration. Plus a uniform continuity, plus the uniform continuity. All right, so you are going to have GT1 minus GT2. You have two integrals. Okay, so this is a linearity, and then if we want to put absolute value, it will be less than or equal to the integral and ds, and when they are close to each other, then this one will be less than epsilon, and then b minus a times b minus a, more or less like this. Okay, it's more or less. You are going to fill the sentences why it is less than epsilon. How do you choose the proper delta so that this condition is satisfied? And this place you must use uniform continuity, because you see you cannot say just let t the distance of t1 t2 is less than delta, then you get this epsilon, less than epsilon, because here you are talking about these 2 points, the distance of these 2 points. You have to make sure these 2 points is less than delta, but this depends on the choice of s. For different s, you may have different delta. Okay, when s changes, this pair of 2 points changes, right? So you need to use uniform continuity. Uniform continuity, then it does not depend on s, and the uniform continuity comes from the compactness and the continuity. All right, so whatever, this should be one of our exercise. Let me find. Yes, this is exercise 1 on page 73. Try to get it. Okay, try to get it. So it's not difficult. When you have uniform continuity for epsilon, you have a delta such that whenever distance is less than delta, ops value will be less than epsilon. And then when you have delta this place, since s are the same, so the distance is equivalent to the distance t1 and t2 less than delta. So you can show that G is going to be continuous by the uniform continuity. You must use uniform continuity. Okay, let's assume this one is already done by you. Well, as we are going to basically show the the interchangeability of integration and differentiation. If phi t, if this formula is proved, then phi partial t is continuous. This integral is also continuous, right? So the g prime will be continuous. So differentiability means if it is equal, then g prime is differentiable. So we only need to set up g prime of t is equal to the integral partial phi partial t evaluated at st ds. So this is what we need to prove. The differentiability is done by this. Continuity is done by the part 1. Okay. Well, let's see how do we prove it. Fix a point T0 in this CD. Fixed point C and epsilon greater than 0, whatever epsilon greater than 0. To simplify the notation in the textbook, the author define phi 2 to be the partial phi partial t. They don't want to use partial phi partial t all the places, so they name it as phi 2. Okay, so just keep in mind phi 2 is a derivative, partial derivative of phi. Phi 2, we assume this partial phi partial t is continuous, so phi 2 is uniformly continuous. On AB cross CD. Phi 2 is uniformly continuous on AB cross CD. It means for this epsilon, there is a delta greater than 0 such that the distance between S prime T prime and ST less than delta implies the ops value of phi 2. This is a uniform continuity of phi 2 of S prime T prime minus phi 2 of ST less than epsilon. All right? Okay, good. Like the first case, if we fix the first coordinate are the same, it implies that phi 2 of ST prime minus phi 2 of ST will be less than delta if T prime minus T, less than epsilon, this is less than delta. Because when S prime is equal to S, this distance, the distance of the point is equal to the distance of the T prime and the T. Right? T prime and T. Okay, so what we have, let's check the integral from T0 to T. Integral from T0 to T, and phi 2 S tau minus phi 2 ST absolute value at ds. Okay, so here I require T minus T0 less than delta. With this condition, T minus T0 less than delta. So when you have T0 and T, this is a big interval. Whatever point between this interval, tau, whatever point, d tau, we integrate tau. All right, we integrate tau. well, we choose whatever tau between t0 and t, then tau minus t0, the distance will be less than t minus t0, will be less than delta. So this point and this point, the distance is less than delta, so the corresponding value, difference of value will be less than epsilon. So it's less than or equal to integral t0 to t, ops value of phi 2 s tau minus phi 2 s t, ops value d tau, and this is less than epsilon, and the t minus t0. T minus t0, right? So that's how we get the inequality. And of course, this part, I never mentioned this t is greater than t0 or t may be less than t0. So we put ops value. We just mean that's the length of the interval. The length of the interval. Okay? So, well, that's what we have. Now let's check what this is. Partial phi 2 s tau. Phi 2 s tau is partial phi partial t s tau. That's actually the derivative along the y coordinate. So phi 2 s tau, phi 2 s tau. Let's use t. Let's use t. It is what? I'm sorry, minus phi. This is t0. My bad. This is t0. It's not t. This is t0. Yeah. In this case, the tau minus t0 has distance less than delta. Yeah, it has to be t0. Okay. Then phi 2 as t0. You check here. Has an antiderivative. What is antiderivative? We're talking about the antiderivative with respect to t, because we differentiate or we integrate the second variable, so it's with respect to t. This one is a partial derivative of phi with respect to t, so it has antiderivative phi st. And this one is a constant, so constant has antiderivative like this, right? Constant will have antiderivative like this, a constant number times t. We just pick up one antiderivative. Okay, so when you have antiderivative, remember AB, f prime of t dt is fb minus fa, the fundamental theorem of calculus. This is a real variable. I don't care what are the image, but this is a real variable. So we do have a fundamental theorem of calculus. Okay, so this one. We can really integrate it. It is equal to this function phi st minus t phi 2 st0 evaluated at t and t0. We can really do the evaluation. Okay, and when t is t, you just get t. When t is 0, you do subtraction, so you have phi st minus phi st0. This is one thing, and this one minus t minus t0 phi 2 st0. Okay, so that's a way how you get the formula in the textbook on page 69. On page 69, you have this one. This is an antiderivative evaluation at the two endpoints. Okay, so we choose this difference and replace it in the ops value. So we have the ops value of phi st minus phi st0 minus t minus t0 phi 2 st0 is less than epsilon over t minus t0. Okay. In this place, we only need one requirement. Remember, all these stuffs starts with this requirement. So we need t minus t0 less than delta. How do you get delta? Delta comes from the uniform continuity of phi 2. Uniform continuity of phi 2. Again, we need uniform continuity. All right, excellent. So now what we can do, we are going to differentiate g. So g of t minus g of t0 over t minus t0. Okay? And it is the integral ab phi st minus phi st0 ds over t minus t0. Right? And then we are going to subtract. Okay, in this place we can divide it by t minus t0, right? So we are going to insert phi, where we have, okay, yeah, this one, phi st, phi st0, and minus we insert this t0 in the integration. Where am I? Okay, this one. ds over t minus t0, and of course we will plus. When you do the plus, you see in the numerator part t minus t0 phi 2 st0 ds over t minus t0. Okay, so after cancellation, you just have this first part. I'm going to call it part 1. And second part plus the integral from a to b phi 2 st0 ds. This difference is cancelled. So that's the reason I'm going to move this term to the left-hand side. I will get gt minus gt0 over t minus t0 minus the integral from a to b phi 2 st0 ds. And I'm going to estimate it and say when t approach t0, this difference will approach 0. So ops value, it is equal to this one. And we put this we put this into the integral, so we get integral, and also we put ops value into the integral. Right? We have such a thing. This is less than or equal to. If we put it outside, it's equal, but if we put it inside, it's less than or equal to. And then this whole difference is less than epsilon if we choose t sufficiently close to t0. So it's less than integral epsilon ds. So it's epsilon b minus a. So that's how you see this epsilon times b minus a in the textbook when you have t minus t0 ops value less than delta. And again, this delta comes from the uniform continuity. You must mention that in the proof. All right, so we are done about the proof about Lebanese rule. Okay, so we will continue the lecture in the next video. In the next video, we are going to see some real concrete computation about the application about Lebanese rule. All right, okay, thank you.